go from current slide. And before we get going, I'll even turn on the, I thought I pressed the button, but evidently it didn't take. There we go. Before we get started, one kind of minor announcement, just to let you know. If any of you were planning to look for me or locate me tomorrow, okay, Friday, I'm not going to be on either campus Friday. Usually on Fridays, I'm on the Birmingham West campus from 8 to 12, at least. Usually there early, usually there later. Not at all there tomorrow, nor am I on this campus tomorrow. I've got an infusion tomorrow, so I will be at the clinic before 8 and will not leave the clinic, I'm sure, until into the afternoon, probably well into the afternoon. So, will not be on campus at all tomorrow. So don't bother looking for me or calling, okay? Now, any questions? Any other things need to be discussed? Okay. All right, we're in Chapter 5, which is, and by the way, let me just say this while I'm thinking about it. I've received only one paper in this course, in this class. Only 2, well, maybe more than 2 first tests. A few of them have turned them in since then, just I don't have them graded. And still 0 second test, but you still got time to work on that. So please try to get these things coming in because we're moving along in Chapter 5, which is analytic trigonometry, and we're in 5.3, solving trigonometric equations. Okay? Now, we did example 4. Okay? But then they skipped example 5, which we have already done, and they skipped example 6, which we're about to do. Okay? But I turn back to this slide so we'd have room to write. So any questions anywhere before we get started? Okay? Now, let me get my pen set up. Okay. Example 6. Now, by the way, if you find this one challenging or you just need a little more than what the book's giving or what I'm about to give, then you can go to larsonprecalculus.com, an absolutely free website. You don't need a code or anything else to get there. To go to larsonprecalculus.com for an interactive version of this type of example. Okay? Now it says find all solutions to the equation cosine x plus 1 is equal to sine x, okay, in the interval 0 to 2 pi. Now, one thing they did, oh, no, they didn't. Okay, 0 to 2 pi. I thought they had a bracket there. There's a bracket on the 0, but a parentheses on the 2 pi. What does that mean?
The 2 pi is an enclosed interval.
Okay, yeah. The 0 is included in the interval, 2 pi is not. It's closed on the 0 end, open on the 2 pi end. So 2 pi, we don't go there. We go right up to 2 pi, but don't hit 2 pi. Now, what do we do with a problem like this? Okay? What's an issue with it? It looks like a fairly simple problem, but what's the issue with it? Okay, yeah, you have 2 different trig functions in there. This would be like saying a plus 1 equal b. How do you solve that? Okay? There's not much of a way to do it. Except that sines and cosines are related to each other. A and b may not be. Okay? How are they related to each other? There's at least 2 ways. One of them's helpful, one of them. All right, the Pythagorean identity. Now, how in the world could you get what is required for a Pythagorean identity?
Square.
You have to have a square. So, what you could do, this is legal in most states, is square both sides of the equation. Okay. Time out. Warning, Warning, warning. Anytime you square both sides of an equation, you have to, at the end of the problem, go back and check your answers. It's not optional anymore, it's required. The reason is you may have introduced what they call extraneous roots. Solutions that really, they look like they're a solution, but they're not. They work for the squared form, but they don't work for the unsquared form. So you have to check your solutions this way. So let's do that. Let's square both sides of the equation. Okay? Because if this is equal to that, then the square of this should be equal to the square of that. So what is the square of cosine x plus 1? Cosine squared x. I agree with the plus 1 part. Plus 2 cosine x. Okay. You have that middle term in there. Okay. If you don't know why, go back and FOIL it, and you'll see why it pops up there. All right. On the right-hand side, what do you have? Sine squared x. Okay. Now, that didn't make things a lot better. In fact, it looks like it made it worse, right? It's a more complicated looking equation. But what can you do now?
Turn the sine into a cosine.
Yes, you can now write this sine squared in terms of cosine squared, and then everything will be in terms of cosine. So what is sine squared in terms of cosine? 1 minus cosine squared. Oh my goodness. You still my heart. Okay. It is Gavin. He is still alive. Okay. He does exist. Okay. Good to see you. Okay. 1 minus cosine squared x. All right. That's equal to cosine squared x plus 2 cosine x plus 1. Right. Now what do we do? Okay, what do you mean by that? All right, here's Jay. It's a good day. We've got everybody but Chris, and Jalen. Usually Jalen will come in sometime. Okay. Now you were explaining what you meant by combined like terms. What were you saying?
You could add the cosine squared x.
That sounds like a wiener to me. Add cosine squared x to both sides of the equation. We're doing example 6 on page 366. Okay? So we add cosine squared x to both sides of the equation. And since we're doing that, what else could we do?
Subtract the 1.
Subtract the 1 from both sides. Why would we want to do that? Excuse me. Why would we want to do that?
Gets rid of the, now just in terms of cosine.
Yeah. You've got a quadratic type equation. Squareds, linears, and stuff like this. You want everything on one side, 0 on the other side. So we can factor if possible. So this adds a 0, that adds a 0. So what do we have on the left-hand side? 2 cosine squared x plus 2 cosine x. And that's all, folks, because that adds to 0. And this equals 0. Now what do we do? Help me help. Pull out common factor. And what do you see as a common factor? 2 cosine x. And what does that leave you with? Cosine x plus 1. And that's equal to 0. All right. Now what do you do?
Find out which one's equal to 0.
Okay, well, you set each of them equal to 0, right? Because here you have an equation that says this thing multiplied by that thing is equal to 0. Now, the only way you can multiply two things together and get a 0 is if one of those things is 0, okay? Or both of them could be, okay? So let's do the first one, and that says 2 cosine x equals 0. Okay? Now, you have that 2 in there. Is that really doing anything for you? Not really, because it can't equal 0, so you can divide it away if you want to. Divide both sides by 2, and that leaves you cosine x equaling 0 divided by 2 is still 0. Okay? Done with the 2 there. Now, what values of x in between 0 and 2 pi would give you a cosine x equals 0? Where is cosine equal to 0? Pi halves and? Not at pi. Pi is negative 1.
0.
At 0 is plus 1. This is multiple choice for me, huh?
Pi halves and 2 pi.
That's at 1 again, same as 0. Remember, cosine is 0 at all your half pi, so that would include and no, that's outside. That's on the left of that. Okay, what's another half between 1 and 2? There's 1 half and
2 halves.
yeah, but that's it. That's 1. 1 half and 1 1/2, right? 3 halves. Yes, at 3 halves pi. So here the x could be pi halves or 3 halves pi. Okay, let's do the other one. Or cosine x plus 1 is equal to 0. And what would you do with that one? Okay, just move it over there. Oh, subtract it. Subtract 1 from both sides. Okay, and that gives you cosine x that adds a 0 is equal to negative 1. And where in between 0 and 2 pi is cosine equal to negative 1? Okay, that's positive 1 there. Okay. Oh, wait. Okay. 2 pi is positive 1, but pi is negative 1. Starts at plus 1, goes to 0 at pi halves, negative 1 at pi, 0 again at 3 halves pi, and 1 again at 2 pi. So at 3 halves, at pi is where it's negative 1. So here x equal pi. And that's the only place in between 0 and 2 pi that it will be negative 1. Is that your answers then? Move on to the next problem, right? No, you got to check them. Okay? So let's go back now. You don't check in this squared form. You check in our original form, which was cosine x plus 1 equal sine x. Okay? Get out of there. Okay. Now, let's try pi halves first. What is cosine of pi halves? 0 plus 1 is equal what sine of pi halves?
0.
What? Oh, wait. Sine of pi halves? Yeah, it's 1. Yeah, absolutely. 1. So you have 0 plus 1 is 1. Yes, that one checks. All right? Pi halves works. Okay? 3 halves pi. What is cosine of 3 halves pi? 0 plus 1 is? And what's sine of 3 halves pi? Negative 1. 1 is not equal to negative 1. You didn't want to do that one anyway, did you? So, you were right. It's not a solution. Okay? How about pi? Does pi work? What is cosine of pi?
Negative 1.
Plus 1 is?
0.
What is sine pi? 0. 0 is equal to 0. That one checks. Okay? So you only have 2 solutions here, pi halves and pi, not the 3 halves pi. Even though that worked for the squared equations, it's extraneous to the original equation. Okay? So, the book agreed, good for them. There is a checkpoint at the bottom, and that audio-video solution to that checkpoint and all the checkpoints are available at larsonprecalculus.com. An absolutely free website. Don't need a code or anything to go there. Go and get assistance if you need it. All right. Any questions on those? Let's move on to functions involving multiple angles. Okay? And the next example involves, they got that wrong, don't they? The next example involves, with an S, trigonometric functions. The example is your noun, and the verb should be singular as well. That should be involves trigonometric functions of multiple angles of the form cosine KU and tangent KU. You could have sine KU or any others KU too. To solve equations of these forms, okay, guess what you do? There's yet another step. First, you solve for cosine, or tangent, or sine. Then you solve for KU. Then you solve for U. So, same as before, we had 2 steps. Now it's a Texas 3-step, okay, Tennessee 3-step, something like that, okay. So, you first solve the equation for the trig function, then you solve for KU, and then finally solve for U. And that's pretty simple, just dividing by K. All right. Here's an example. 2 cosine 3t minus 1 is equal to 0. What would you do first? Help me, somebody. Add 1 to both sides. And that gives you 2 cosine 3t, that adds to 0, is equal to 1. Okay, now what? Help me. Somebody. Divide by 2. Okay, that gives us cosine 3t is equal to 1/2. Okay? All right. Now what do we do? We've solved for the trig function. We isolated the trig function, got it by itself. Cosine 3t is equal to 1/2. Now you solve for the argument of the trig function. Okay? What does that mean 3t must be? Where is cosine equal to pi halves? And on this one, they don't give any limitations on it, so we're going to have to do those in pi, or 2 in pi type thing. So where is 3t? Okay, what value of 3t would make cosine 3t equal 1/2? Pi thirds. So 3t is equal to pi thirds. Is that the only place? Yes, in the fourth quadrant, because cosine is positive in the first and the fourth quadrant. So it would be pi thirds short of the horizontal axis, which would be where? Five pi thirds, you're right. Because 6 pi thirds is 2 pi, so that would be 5 pi over 3. Okay? But, because they didn't put any limitations on us, we also have to do the plus. What is the period for cosine? Okay, so we have to do 2 n pi. And this one too, plus 2 n pi. Any multiple, even multiple of pi. Okay? So those are our 2 solutions for 3t, but that still doesn't tell us what t is. Now we have to figure out what t is. What do we do? Say again?
Solve the equation for 3t.
And how do you do that?
Set 3
Okay, do what now again?
You solve what you have.
Okay, how do you do that? How do you undo multiplying by 3?
Divide by 3.
Yes, divide by 3 or multiply by 1/3. So here I'm going to divide by 3. Here I'm going to multiply by 1/3, which is the same as dividing by 3. And here I'm going to divide by 3. Same thing here. This is also 3t. So I'll divide by 3, multiply by 1/3, or divide by 3. Okay, so what's my answer? This leaves me t is equal to pi ninths plus 2/3 in pi. Or 5, I can't read my writing here. That's a time sign, I think. No, that's a 1 there, okay. That's, this 3 goes out. T is equal to 5 ninths pi plus 2/3 in pi. All right, there we have it. You have to do that other part. So you have to put the general form here before you divide. So this part has to be divided by that 3 as well. Does that make sense? Comma may be confusing there. Or, I'll put that. All right. Let's see how the book did it. All right for me to erase? Everybody got it? Yay or nay? Okay. All right. First thing they do was write the problem over again. I'm glad they took the space to do that. Then they added 1 to both sides, just like you did. Then they divided by 2, just like you did. Now we've solved for cosine. Okay? So now we solve for the argument of cosine, which is 3t. Where, at what values of 3t is cosine equal to 1/2? And you were absolutely right again. 3t is either pi thirds or 5/3 pi. But because this had no limitations on it, we have to put our plus 2 in pi, because period for cosine is 2 pi. So any multiple of 2 pi. But you're not through. You want to solve for t. Okay? So then you divide everything on both sides by 3, which in the first case is multiplying by 1/3. Okay? So that gives you t is equal to pi ninths plus 2n pi over 3, or t is equal to 5 ninths pi plus 2n pi over 3, where n is any integer. That's your general solution. Not any real number. That wouldn't make sense, but any integer. Positive or negative integer. All right, good deal. Any questions on that? Everybody see how to do it? Okay. That was example 7. There's a checkpoint after example 7, and right there you'll notice there's audio-video solution for that checkpoint at larsonprecalculus.com. So let's do example 8. All right, we'll do example 8 right here. Here's an equation. 3 times the tangent of x over 2 plus 3 is equal to 0. How do you solve that one? Okay, start with subtracting 3 from both sides. We're trying to isolate the tangent. Subtract 3 from both sides, and that wipes out the 3 here. So that gives you 3 tangent x over 2 is equal to negative 3. Now what? Yes, still trying to isolate the tangent, so divide both sides by 3. Okay, and what's negative 3 over 3? Negative 1. So now we have a tangent of x over 2 is equal to minus 1. So now we solve, now that we solved for tangent, now we solve for the argument of tangent. Now, at what values of x over 2 would tangent equal negative 1? Where is tangent equal to negative 1?
7 pi over 4.
Second?
7 pi over 4.
7 pi over 4 would certainly be 1. I would have said negative pi fourths. That's the same as negative 7/4 pi. So x over 2 must equal 7 pi over 4. Almost 2 pi, but not quite. But because there's no limitations on this, what would you put? Okay, no, there's not another place. In one cycle of, you're right, it is there. Okay? Huh? No, okay, think about it. Tangent is positive in first, negative in second, positive in third, negative in fourth. Okay, so you're right. It is a pi fourth pi, but it's repeating itself. The period for tangent is pi. So you can cover that by just saying plus n pi. Okay? That's not making sense, is it? No. It's negative 1, so not at pi fourths. It's negative in the second quadrant.
That's what I said. That's 5 pi 4.
No, 5 pi fourths is in the third quadrant. 3 pi fourths. Yeah. And if you do subtract off 4 fourths pi there, you get 3 pi. Okay. So plus n pi. Okay? Because tangent is periodic by pi. Now we need to do what? Now we want to solve for x. Not for the argument, but for x itself. So what do? Multiply everything on both sides by 2. I'll just do it there. And now we get x is equal to what? Help me. 7 pi over 2 plus 2 n pi. Very good. Perfect. Way to go. Now, they didn't quite do it that way, and it's fine. They went straight to the second quadrant rather than the fourth quadrant. And in the second quadrant, it would have been 3 fourths pi. You see, that's still covered here because you add or subtract 4 fourths pi here, you get 3 fourths pi. So that's covered. You know, it's absolutely covered. But the one they did in the book was x over 2 is equal to 3 pi over 4 plus n pi. And then that would have been x equal 3 halves n pi. 3 halves pi plus 2 n pi. Right. So that's why theirs looks a little different. It's the same answer. It's just 1 n pi away. So actually 2 n pi's away. Okay. 2 pi away. All right, good deal. There's your check point. I would have written it yet another way. I would have said negative pi fourths. Because I think of that as being my tangent function. It's positive here and negative here. I would have said negative pi fourths. Same answer, okay? 7 fourths pi, it's the same angle as 7 fourths pi, but it's the same, as that. So it still works. There is a checkpoint. Please do that as well. Any questions? What we've done so far? All right. That was example 7 and 8. Why was I not there? Okay, no, we were there. Okay. Next subtopic is using inverse functions. Now, I won't say anything yet, but let's continue. Okay. They're not going to lead us in with this, they just give us a problem. Secant squared x minus 2 tangent x equal 4. There's an equation. They call it the original equation. It's an equation. Okay? What in the world can we do with that? You see any problems with it? Yeah, you have two different functions. So that's like having apples and oranges, right? I like them both. Okay, what do we do with it?
Well, then you put secant squared into tangent as the protagonist.
And what would that be?
Tangent squared
Plus 1, got it. Now I didn't need the parentheses there, so I think I'll take them out. But that is what the secant squared x is. And then subtract from that 2 tangent x, and that's x, and that's equal to 4. Okay, now what?
Subtract the 1 over.
Okay, I think I'd go the other way. Because you got a quadratic. You want everything on one side, 0 on the other side.
Subtract the 4 over.
Yeah, let's subtract the 4 over. Now, I would move the 1 over, if that's what you meant, to the end of the problem, and make it tangent squared x, because we're subtracting 4, minus 2 tangent x, and then that would be a minus 3, right, is equal to 0. That's what you want. You want, for a quadratic or higher, you want everything on one side, 0 on the other side. So if you can factor, then it's doable. Okay? And that's the next question. Is this factorable? What's your answer? Maybe you don't know until we try. It would be a tan x times a tan x. These are x's, aren't they? Okay, I agree with that first step. What about the signs? Where do we look to determine? The sign of the last term is negative, so that means these two have to be, nope. If they're both negative, that would be a plus. Right? So, help me somebody. One's negative and one's positive, okay? Now, you want two numbers that multiply to be 3, but because they're different signs, their difference is 2. Well, the only two numbers that multiply to be 3. Absolutely. It's 3 and 1, and put the 3 with the minus, because the minus wins here, and the 1 with the plus. You can multiply it through and check it. It checks. Okay? Now what does this yield for you? Either tangent x minus 3 equals 0, or tangent x plus 1 equals 0. One or the other of those have to be true. Maybe both. Okay? Now, what do you do to the first one? Add 3 to both sides. And that gives you either tangent x is equal to 3, because that adds a 0, or subtract x from both sides, and that gives you tangent x is equal to negative 1. Do you know the answer to either one of those?
The one on the right would be
Okay?
Or 3 pi over 4.
Yeah, okay. So we'll put 3 pi over 4, x equals 3/4 pi. I would have said negative pi fourth, but it works. But that's not the only one. It is in one period. But so to account for all periods, since there's no limitation here, plus n pi. Okay, because the period for tangent is n. But that other one, don't think I know that one, do I? I know for square root of 3, but for 3, don't think so. So what do we do? Oh, that's why they said using inverse functions. If you do the inverse of this, you have tangent x equal, okay, wait, back off. All right. Here's basically what you do. I don't know if you're used to doing this. Take the inverse tangent of both sides. Okay? And this undoes the tangent, so you're left with x equal, and all you can put here is inverse tangent of 3. Okay? That's your answer, plus n pi. Okay? Because inverse tangent of 3 is only one value, something between pi fourths and 2 pi halves. Because at pi fourths it's 1, and at pi halves it's going to infinity, so it doesn't have an answer. So it's somewhere in between there, but then every n pi after that is another. So there's one solution, or here's a second solution. Okay? Now, there it is. Couldn't find it on the page. They say arctangent, whatever you want to call it. Okay? So let's see how they did it. I think it's awfully similar. Okay? First thing they did, just like you did, do the Pythagorean identity for secant squared x, and that gives you 1 plus tangent squared x minus 2 tangent x. And they went on and subtracted the 4 from both sides to begin with, so that gave them equals 0. Then you combine the like terms, and that gives you tangent squared x minus 2 tangent x, and the 1 minus 4 is minus 3 equals 0. Then, just like you did, they factored and got tangent x minus 3 times tangent x plus 1 equals 0. Setting each factor equal to 0. The only one you get for this, because that's not one of our favorite angles that we know an answer to, we just do arctangent 3. Okay? This is between minus pi halves and pi halves. Remember, you can't go outside of that for tangent, or for arctangent especially. Okay? So then the other at minus 1, you know what that is, and that's minus pi fourths. Okay? Now, you said 3/4 pi, that's okay, because we're going to add the n pi. And this is what sort of drives me nuts. In the earlier ones, they were not doing the negatives. I said I would have, and here they're using the negatives. It's fine. It's perfectly fine, because 3/4 pi is in that. If you think about it, all you do is add 1 pi to this, which is 4/4 pi, and that would give you 3/4 pi. So they're all included in there. Okay? So those are your two solutions. Now, if you want an approximate answer, you'll never get an exact answer to arctangent 3, but if you want an approximate answer, you can plug that in and get that value. And that's all they do. Okay? Now, there's a checkpoint. I highly recommend you do the checkpoint as soon as you can after class while it's sort of fresh on your brain. Okay. So let's back up. Since they skip example 10 and 11, let's do those two. Now, do y'all like doing them, or is this just wasting your time? Okay. Or do you even care? Okay. Don't answer that question. I might be hurt. No. Okay. All right. Let's do example 10. Solve this equation. 4. No, I can't. I'm reading the wrong one. Okay. Example 10. Find all the solutions of sine squared x minus 3 sine x minus 2 equals 0 in the interval from 0 to 2 pi. Okay, in other words, the first period. Okay, what would you do first? Wow. Factor, yeah. There's nothing you have to change because you're all in terms of the same trig function. You got it equal to zeros. You don't have to move anything there. So let's see if this baby will factor. Okay, if it will, we're going to be pretty good. What's the only possible factorization for sine squared x? Sine x by sine x. Okay, that was easy. Now, where do we look for our sines? Okay, one's going to be positive, one's going to be negative. And then the only, whoa, don't think this is going to factor, is it? Not in the real number system. So that didn't work. So what are we left to do now? Quadratic formula. And the only little catch here, it's not going to be x equal, but it's going to be sine x equal. And what would you put there? Negative and negative 3, which is a positive 3, plus or minus the square root of which is 9. What follows that? Minus 4 times what? 1 times negative 2, is that what you said? Okay. All divided by, which is 2. All right. Well, surely that should have factored, shouldn't it? No, okay. Let's continue. Looks like it would have, if I did it right. Okay. So this will be 3 plus, or, oh, no. No? What do we have inside the parentheses? Oh, yeah, I'm right. It wouldn't factor. What you got inside the parentheses? 9 plus 8. Okay, I'm feeling better about it now. Over 2, and this will be 3 plus root 17 over 2, and 3 minus root 17 over 2. There are 2 solutions for sine x. Now, Here we need to use our calculators. Normally, not absolutely necessary, but why do you think we need to here?
These values are on the unit circle.
What's that?
These values aren't on the unit circle.
Okay, that might be part of it. I think I understand what you're saying. But in other words, either one or both of these cannot be outside the range of one, outside the range of signs, which is more than +1 or less than -1. Okay, so we got to see what they are. I'll tell you right now, the second one will work because square root of 17 is just a little bit more than 4. 3 minus 4 will be a little bit more, less than -1, or and then divide that by 2. Yeah, that's going to be no problem. It's the one on the other side that I think we have a problem with. Square root of 4, something a little bit more than square root of 4 plus 3 is going to be something more than 7. And 7 halves, not going to happen. This will not give us a usable solution. You see why? Sin x can't be anything greater than 1. That's going to be greater than 1. This one will give you a solution. So now we can say x is equal to the inverse sine of 3 minus root 17 over 2. Okay, plus 2, we don't need a plus 2 in pi. But here's the nasty part. What's the other side of that one? Okay, that's in the third quadrant, but you also have one in the fourth quadrant. No, that was in the fourth quadrant. You also had the one in the third quadrant, and that's a lot, somewhat more difficult to do. And it's not a simple All right, sorry. You can't do that either. I just realized. Oh, wait, you can. Yeah, but it says note that this solution is not in the interval 0 to 2 pi. It is in there. Yeah, okay. Oh, yeah, you're right. No, it isn't, because it's outside. This is a negative. The inverse sine is a negative x, okay? Because remember, for inverse sine, all your negatives are over here left of 0. So what you have to do is add to that 2 pi, okay? Add to inverse sine of this 2 pi. Okay. Now, Now, I should probably draw it for you, but since they've already drawn it in the book, I'm going to try to do it here. I'm sorry, people at home, I'm being lazy. Okay. This answer that we got here is over here. That's not on the interval from 0 to 2 pi. 0 to 2 pi goes right through there. is heavy. All right. So you add 2 pi to that, and you get this answer. Okay? Now, all right. Now, the answer that you had they're doing some really strange things here. I'm trying to see why. Okay. All right. Here's the answer they have. Okay. Add 2 pi to it and you get this one, and that is an interval 0 to 2 pi. Okay. Now, that's in the fourth quadrant. In the third quadrant, what you do is take pi and subtract the same thing from it, because you see, here you are at pi, right here, and where you added that here, subtract it from, subtract that value from pi, that they're calling it, this is winds up being a negative number, and it's negative 0.5963, okay? So take pi and subtract that number from it, minus a minus gives it a plus, makes it a plus, so it's pi plus that amount. So, it's so hard to hold. Okay. The same amount that you're subtracting here, you're adding here. You see, this is equivalent to that. So you add that same quantity here, negative 0.5963, to pi here, and you get this one. Subtract it from 2 pi here, and you get that one. Okay? And which is the same as just adding 2 pi to this number. It comes out that way because of this. Okay, this angle, whatever it is down there. It's a negative angle. Okay? Well, that's not in the interval 0 to 2 pi. So you add 2 pi to this negative angle, and that's where you get that one. Same angle over here gives you the same result. So you take pi minus this angle, but that minus is already a thing, so add this angle to pi, and you got that one. So there are the two places. Pi plus that negative number, and 2 pi plus the negative, okay. Pi plus the value of that, or 2 pi plus the negative of that, okay. Both of those will give you the answer. So that's why they have two answers there, and they're not really related to each other that much, but they are by the angle that they're missing. Okay. In other words, this is your reference angle here. Okay. So take the negative here, add 2 pi to it, and you get that number that's between 0 and 2 pi. Take the value of this here and add it to pi, and that gives you the angle over here. Two angles have that same sign. And they're both related to this, but in sort of different ways. Okay? One is the reference angle and one the other. That one's a little bit trickier. Okay, so watch out for that. So there's your, and there is a checkpoint, and I bet you that's going to be something almost as squirrely. Okay, then there's example 11 is another one that's rather squirrely. So let's do that one as well. Okay? Actually, this one may not be as bad as you think. The surface area S in square inches of a honeycomb cell is given by this. This is the surface area of a honeycomb cell. 6HS, okay, and I wish they showed the picture because I sure am not going to draw it, but I'll hold the book up for you to see it, plus 1.5 S squared times, this is the squirrely part, square root of 3 minus cosine theta divided by sine theta, okay, and that's good for 0 degrees less than theta less than or equal to 90 degrees. Okay. Now, whoa, goodness, I don't move this. I just messed something up there. There, that's better. Okay, let me do my book. And kinda, maybe in some little way, sure. Okay, now what is the S? S is this little angle here. The base of that honeycomb is a hexagon. Okay? If you ever notice a honeycomb, they're six-sided cells. So there's the base, is a six-sided cell. And S is the length of any one of those sides. Okay? Now, H is the depth of that cell. So that's where your 6. You have 6 sides and 6 that, so 6 times HS, those little rectangles there, that's going to be your the area of the little rectangles. But you see, they're not rectangles on the sides here. They have sort of a rooftop. I think this is inverted, but you get this general idea. And that's where the second part comes in. 1.5 S squared. Okay. I'm not going to tell you how they get this because it's really too complicated to figure. I'm not even sure I could figure it, but they're telling you this is it. So the 6HS is simply the rectangular part of all 6 of those sides. That's where it is, H times S. Okay. But then you take that S and you fiddle around with it, and the sines of it, the cosines of it, S squared, yeah. That gives you the rest of the surface area. That's the rooftop and the other pieces in there. Okay? You don't need to know how they got it. Just that's what it is. They told you that's what it is. Some entomologists figured this out. Okay? So, we'll leave it like that. Where H is 2.4 inches. Big deal, who cares? S is 0.75 inches. Okay? And theta is the angle shown in the figure at the right. Okay? And I'm not about to draw it. Okay? So let me point it out to you here. Sorry, people at home, you can't see the book. Hopefully you got your book, so you look in the book. Theta is that angle there, that housetop that you have there, that's that angle theta. So that's coming into play. So that's all we need to know. Okay? That's what we think of. What value of theta gives a minimum surface area? What value of theta gives a minimum surface area? And the theta has between to be in the first quadrant 0 to pi halves. Okay? Now, what they're going to do is plug in the numbers that they have here, and this surface area is then going to be 6 times 2.4 times 0.75. If you got a calculator, you can check them on it. See if that gives you 10.8. 6 times 2.4 times 0.75. Seems reasonable. 3/4 of 2.4 would be 1.8 times 6. Yeah, I think that's right. Okay. Plus 1.5 times 0.75 squared. That seems reasonable to be 0.84375. That's a pretty small decimal. I mean, reasonable decimal, but I mean, lots of places there. This part leaves the same. Square root of 3 minus cosine theta over sine theta. Okay? Now, I don't know any way to solve that analytically. Okay? And I don't see any way that you could. Now, when I read that the first time, and every time, I think, only way you can solve this is by taking a derivative. Wait, this is pre-calculus algebra. We don't have derivatives yet. Okay? So guess what they do in the book? They draw it on a graphing calculator and find the solution. Well, I don't have a graphing calculator up here in the classroom. I don't know if any of you do. If you want to play with that, you certainly can. And you should get the same thing they do. And there the angle is, they say, 54.7356 degrees. Yes, I know that those honeybees are up there making that exact measurement to the nearest 10,000ths of a degree. They know what they're doing. So I'll leave that to you. We're not going to spend any more time on that. There's a checkpoint there. That finishes the section. Let's do the vocabulary. All right? Fill in the blanks. When solving a trigonometric equation, the preliminary goal is to blank the trigonometric function on one side of the equation. What do you reckon that could go in that blank? In solving a trigonometric equation, the preliminary goal is to blank the trigonometric function on one side of the equation. I can think of one word that works really well. There may be others. I would say isolate. Isolate. Get it by itself. Get everything else on the other side. Okay? Ultimately, that's what you're trying to do. That if it's not in a squared form anyway. Number 2, the blank solution of the equation 2 sine theta plus 1 equals 0 is theta equal 7/6 pi plus 2n pi or 11/6 pi plus 2n pi, where n is an integer. What do they call that when you put all those possibilities with the n pi's, 2n pi's? The most senior officer in an army is general. That's called the general solution. Okay. Picky. That's just nomenclature, vocabulary. Number 3, the equation 2 tangent squared x minus 3 tangent x plus 1 equals 0 is a trigonometric equation of the blank type. Quadratic type. Maximum exponent is 2. Number 4, a solution of an equation that does not satisfy the original equation is an blank solution. You get them when you square both sides. Again, it's sort of a picky word here. If you look back at example 6 in the very last sentence before full sentence, or last 2 sentences there, they use the term extraneous. To me, really picky vocabulary on this one. Homework exercises. Any of the odds 5 through 9, all of those are found at calcchat.com. Also in the back of your book. Any of the odds 11 through 27, they're all at CalcChat. 13's at CalcView. Any of the odds 29 to 37, they're all at CalcChat. 29's at CalcView. Any of the odds 39 to 45, they're all at CalcChat. Do 47 is at CalcChat. Do any of the odds 49 to 57, they're all at CalcChat. Do any of the odds 59 through 69? They're all at Calc Chat. 61's at Calc View. Do either 71 or 73? They're both at Calc Chat. 73's at Calc View. Do either 75 or 77? They're both at Calc Chat. Do any of the odds 79 to 83? They're all at Calc Chat. Do 85? It's at Calc Chat. Do 87? It's at Calc Chat. Do any of the odds 89 through 93? No, I'm sorry. Whoa. They go on and on. Through 95. They're all should be at Calc Chat. There's a true false. 99 should be at Calc Chat. You can think about 101 and or the graphical reasoning in 103. And let's see, how are we doing on time? We're almost out, so we'll pick up with section 5.4 next time. Now, here's why I was a little late coming to class, and I'm glad it didn't come to pass for one reason. At one point, oh, there it is. I was stopped in the hall and told by an instructor that we were supposed to have a fire drill this morning at 10:30. I'm glad they didn't, because I'm in short sleeve shirt, you're in shorts, and we'd have been standing out in the cold. And has it started raining yet? It was on the way in. Cold and rain, I would have been really upset to have to stand out there to wait for them to fiddle around for a fire drill. And I don't need to catch a cold. I don't know if I would have, but I don't need that with an infusion tomorrow. So I'm glad they didn't do it for all of our sakes, but especially for Dawson and me, because I think we'd have been quite cold out there. Y'all might could have lived okay, but it would have been miserable. So glad they postponed it until a nicer day. They will not postpone a fire, though. If we did hear it go off, we'd do the procedure. Okay? All right. Take care. Well, have a good weekend.